वालेकुम अस्सलाम। जी अल्हम्दुलिल्लाह। नेक्स्ट लेक्चर जो है ना वो okay, I think it's time to start today's lecture. Although we have only one student here in the physical classroom, but I hope there will be some online students. Yeah, we have some more students. Okay. Yeah, today's lecture we will talk about regular expressions and finite automata context-free grammars. These are kind of. Can someone open the door, please? Okay, so we have more students popping in. Press the key button. Can you press the key button? Okay, yeah. So yeah, we will be talking about formal languages, regular expressions, and what the regular languages and regular expressions are, and why we need them. And before describing and going into details of these, there is some information, as you might have expected, that this will be the final lecture content-wise. The next lecture will be the last lecture, but that will be about examination. So the written exam. So you will get some information, what kind of question there will be. I will upload some of the previous examination papers to the Moodle page, so you can just go through it and get an idea like what kind of questions you are going to attempt in the final examination, which is I think scheduled on 26th of this month. And there might be some change of time, so you should look at the online exam registration system for the exact information, like what time and location for the exam. But I think it's in the beginning I told something like from 8 in the morning until 1 o'clock, but according to the room reservation system, the time has been changed. It's from 2 o'clock until I think, yeah, so 5 hours. You still get a 5 hours, but it's not in the morning, it's rather in the afternoon. But you will get more details about the examination in the coming lectures. The coming lectures about the examination, it will be given by one of my colleagues, Dr. Jonas Lundberg. He's the most senior teacher in this course. He has been teaching this course for last many years, so he knows a lot more than me. And yeah, and because I will be traveling outside, so I cannot take part in the next lecture. Okay, so that's some practical information, and also I hope you have been done with the third assignment, and you will get the fourth assignment later in the evening today, so you can start working on that. Yeah, so. And beginning with today's lecture, have you used regular expressions? Some of you, are you familiar with these concepts? Any idea? Yeah.
Yeah, use them
So for what do you use?
That's only for either replacing some specific text on for a file,
Mm-hmm.
or just searching for specific things, validating.
Yeah, to replacing some kind of subtext in your file or searching for a text. Yeah. So regular expression, they are mainly supported by many programming languages, and they are mainly used to search, to define. You can define a pattern by using regular expressions, and then according to that pattern you can search in a file or in a sequence of strings, and then to recognize those patterns we use finite automata, and the context-free grammars and the regular expressions, they are kind of similar but not exactly the same. Both we use to define some kind of language, and beginning with before going into the details about how can we use context-free grammars and regular expressions to define a language, it's maybe interesting to see what a programming language is, or what a language in general is. So how do you define a programming language like Java? So, I mean, if you have been asked to define something, a language similar to Java, that that should include all the possible, correct Java programs, as well as exclude the non-correct Java programs. So, how will you begin with? What should be the starting point? Probably that's one part, defining with the keywords. Methods, yes. And then this is more like a bottom-up approach. So starting with the smaller parts, and then, because usually you have keywords defined within, you use the keywords within a methods, and then the methods are defined within the classes. So of course, I mean, the approach that you described is more like a bottom-up approach. You can choose that one as well. But here is an example of a top-down approach. So where you start with you know that every Java program consists of at least one or more classes. So you can start with defining what a class is, and then and you know that to define a class for a similar to Java, you need this this thing, public class, and then you need these are the keywords, public class, and then you need identifier. So it means that you need to define keywords, and you also need to define the identifiers. We already covered them a lot when we learned about object orientations using Java. And then, of course, after this class definition, you will have maybe a number of different methods and member fields. Okay, so that's one approach. And then a part of I don't know what's wrong with the projector screen. So but I hope you will be able to get the most part of it. Let's see if I can zoom out a bit. Or maybe we can just use like this. No, but it still goes on. Yeah, never mind. And then, the other details, like this is more like a high-level details of your program, and then you have often another part of the language which provides you with the tiny details, like as you said, that smaller pieces of your program, like identifiers and keywords. So usually you have like two parts in your language definitions, one with the high-level structures like classes and methods definition, and then you have a part that covers up with the low-level details like keywords, identifiers that you use to build up statements in your program. So for example, we have we need to specify that an identifier, and then we define some rules, like an identifier should consist of, it could contain only some special characters, letters, digits, and maybe some languages allow some other characters. So for example, in Java, which other characters you can use other than digits and letters for the identifiers? If you have to define a variable, and if you want to define an identifier, so what characters can you use in Java? You have been programming with Java for many times, other than digits and letters. Sorry? Basically, everything. Yeah, no, I'm asking about the names, for the identifier names. So you can, which, for example, from the alphabets, A, B, C, D, that are your letters, and then you have a digits. Can you use special characters, like at the rate of, or maybe and, hash sign? Can we use them? Sorry? Yeah, not for naming. So that was yeah, my question. So I mean, of course, these are the rules that you need to define in your language definition, that what is allowed and what is not allowed over there. And also, often you have rules like an identifier or a variable name should start, should start with a letter, and then afterward you can use digits, but not the first character cannot be a digit. For example, in Java, this is not allowed, that every identifier or variable must start with a letter A, B, C, or maybe underscore or a dollar sign, but not with the digits 0, 1, 2, 3, or 9. Okay, so that this is how we normally define a language. And if you look at some of the language specifications, for example, if you look at how the Java specifications are defined, so you will find constructs like this. So these are, we will learn about more about, because this might look a little bit strange for you guys if you are not familiar with the context-free grammars. So we can read this as like a program, and then program consists of one or more. This plus sign says like at least one or more than one class declaration, and then we define what class declaration is. And then we define like the keywords. So these are more like kind of named expressions. And then we have keywords, public class, identifier, left bracket, so field declaration. So we have to define a number of such specifications using according to the context-free grammars rules. And often for tiny details, we use regular expressions. And we will see that both we can use regular expression and context-free grammar to define a language, but there are some differences. Context-free grammars, they are more powerful. They can, you can define any language that can be defined by a regular expression. You can also define it by using a context-free grammar, but not the other way around, because regular expressions have certain limitations. You can use it only to define certain constructs, but not all the constructs. But however, using a context-free grammars, you can define most of the constructs in your language definitions. And normally we use regular expressions for tiny details, as I said. For example, to define identifiers rules in a language like Pascal. So we could say that an identifier may contain, here we have some definitions. So what is a letter? Letter is consists of alphabets from A to Z. That could be in the small case, or it could also be in the uppercase. So anything from A to Z could be is defined as a letter. And then we have a digit, basically from 0 to 9, all the digits. And here we have a Pascal ID which specifies that it should start with a letter, okay? And then after the letter, it could come either, you can use either a letter or you can use a digit. And this star specifies that, at least you can have one letter beginning with, and then this star specifies 0 or more. So because maybe you can name an identifier just a single character, like int A or int B, int X, Y, Z. But of course you can use more letters or digits in your identifier. So for example, integer marks, in that case you have a more than one, but okay. So what is a language in computer science? Yeah, we already talked about this a bit. However, if we have to formally define a language consists of three things. We have symbols, that are the basic units. of your language, and the smallest identifiable units. And then we have the alphabets. It's a set of symbols, a finite set of symbols that you use to define your language. And then we have strings, and the strings are basically a sequence of symbols over the alphabet, and it's a finite sequence of symbols. So here we have an example. For example, if we have an alphabet set A and B, and using these alphabets, and here A and B, these are the symbols, and the set of these symbols is this alphabet, and using these alphabets we can make any number of strings by combining A and B. For example, A, B, A, and A, B, B, A. So you can come up with infinite number of different string sequences by combining these. And also, if you see, for example, for a binary language, you have an alphabet 0, 1, and then combining 0, 1, you can come up with any number of different words. Okay, so in simply, we have the one thing that you need to remember is that every language has a smallest unit in the language are called symbols, and then the set of symbols is alphabet, and then on that alphabet you can define a sequence of symbols which are known as strings. Is it okay? Okay, and then we have some concepts about the language. The length of string we denote it using this operator, and it's basically the number of symbols in a string X. So for example, if you have a string and if you want to find out the length of this string, so it's the number of symbols in that. So it's some 1, 2, 3, 4, 5. So it's length. If it's like X, then the length of X is equal to 5. And so here's another example. So and then we have a special string denoted by the empty notation, and it's a special string with the length 0. You can have if you want to. Sometimes you need in a language that to specify a string with length 0. We will see in what cases we need this kind of special string. And then we have a closure of alphabets, sigma. We use the sigma notation for the alphabet, and it's basically the closure of an alphabet is an infinite set of all strings over the alphabet. So for example, as I said, that if you have an alphabet consisting of only 2 symbols, but you know that you can combine these 2 symbols in an infinite number of combinations. So starting with the empty string, then A, B, and then combining in a number of 2s, and then 3s, and you can keep on combining with them. So the closure of an alphabet is always like an infinite number of. So you cannot define all the possible combinations. Okay, and then if we have to formally define this, we can say that a formal language L over the alphabet sigma, denoted by L as a function of sigma, is a well-defined subset of closure. Okay, so every language will be a subset of closure of the alphabet of that language, because you cannot have. If you usually, of course, if we ask you, can you define a set of all the possible Java programs? Is it possible? No, because we cannot specify a finite set of Java programs. There could be millions of billions of Java programs can be written. Even if we ask in this class, you guys can come up with millions. If the task is assigned you to come up with all the possible Java programs, no, it's not possible. Usually, in the languages we have infinite sets. Okay, and but the most important concepts are the basic concepts that you need to remember is the symbols, and then you have the alphabets, and then you have strings, and and the string length. And then we have a common language related problems, and the first problem is defining a language L over some alphabet Z. As I told you that in the beginning, that it's not, the languages are often infinite set of strings over the closure, and one of the problem with this is that we cannot define all the possible strings or in case of a Java programming language or some programming language, all the possible number of programs or the codes, because there are infinite number of programs that could be written by a number of different users of that language. And then we have a problem with the common language problem is recognition. So for example, you have a string, and then you have a language L, you have a string S, and then you want to verify that whether this string belongs to that language or not. So this can be seen as some phrase in a natural language. For example, you say hello, and then you want to recognize if hello belongs to Swedish language or not. Okay, so this is the recognition problem. So for example, and this is very important. For example, first step to compile your program is that you need to recognize if it's a correct Java program or not. So for example, if you are writing a compiler for a Java, and to transform that your source code into a bytecode, you first need to recognize that if it's a valid Java code or not, if you can recognize it as a Java code or not. So we have this problem. So, and then of course it's either yes or no. Either the program belongs to a language or it doesn't belong. Either a string belongs to language if it fulfills the rules according to the language, or it's not. And then we also have a parsing problem. So in the parsing problem, that's also parsing is used in the compiler construction thing. So where you, along with the recognition, you also build a visual representation of your program. So and normally we use the parse trees or abstract syntax trees, which are basically a representation of your code in terms of nodes and association between the nodes. Okay. And then we have the regular language. It's we have looked at the formal languages, and we learned about some basic concept about the languages and what are the basic building blocks of the languages. And then we have the regular languages. These are the most simple kind of languages, and these languages are these are easy to understand and define and work with. And we are often these regular languages. These are defined using the regular expressions. Okay. And and each regular expression defines. So we can say that if you have a regular expressions, and then you can say that the number of strings that are recognized by these by that regular expression, the set of those strings forms a regular language. Right? And what is a regular expression? So regular expression is a pattern constructed by three basic operators. Okay. So it's like, you know, you are already familiar with the concept of expressions when we have like arithmetic expression. So here we have a regular expression, and the regular expression we have, the symbols, the basic symbols, and then we have some constructs are the operators, and the basic operators we have selection operator. This is either A or B, and then we have a concatenation operator, which means that whenever there is an A, the A must be followed by B. Okay, you cannot use A as a standalone or alone. And then we have a star operator, which says that if you have an A with a star, it means that you can have a 0 or more than 1, 0, 1 or many number of A's. Okay. However, these operators, when you use these operators together to write a regular expression, we have some priorities between the operators, so operator precedence, similar to what we have in the arithmetic operators and the other operators in Java. This one, the star operator, it has the highest priority, and this guy, the selection operator, it has the lowest priority. So for example, if we have written something like this, A, B, star, and then B star A, so it means the first of all, and the highest priority will goes to the star, okay, and then the second priority is to the concatenation, and the lowest priority will be going to the selection operator. So this could be, I mean, you can of course write this in this way, but since by default this has the highest priority, so we can just remove the parentheses. And in short, we can say that every string that matches the pattern R. So here we have a pattern R. This is our pattern. Every regular expression defines a pattern. And yeah, and if a string can be recognized by a pattern R defined using a regular expression, then it's a part of a language which is defined by this yeah, regular expression R. Yep. Yes. Maybe. Yeah. No. Good idea. Yes. Yeah. Yeah. Thanks for this suggestion. And then, yeah, we have here is just a summary of what we have learned already, and then some examples. Okay. We know that each alphabet defines a set of regular expressions. So whenever you have an alphabet, and based using that alphabet, you can define a set of regular expressions over that alphabet. So this means that if you find something like that, it means that it is a set of regular expressions defined on this alphabet. Okay, and this alphabet could be anything. It could be like, yeah, depending on your language. So what alphabets you allow. So it could be, for example, if you have a language that consists of only the letters, so you could have like, the alphabet could be like A, B, C, or it could be A to Z, or the alphabet could be, yeah, both A to Z and then 0 to 9. So it depends on what kind of language you are going to define. And then yeah, each regular expression, this small r, this denotes to a regular expression, belongs to this set of regular expression. It defines the regular language, and we specify the regular language using this capital R, and it's a subset of closure on the alphabet. Remember that this closure on an alphabet is a set of all the possible, is an infinite set of sequences on of symbols or the strings on the alphabet, and it means that the regular the language will be a part of or the subset of this closure on that alphabet. And you can find out yeah, by matching the strings by matching the strings to the pattern that you have defined. We will see the examples, and then I think it will become more clear that. So for example, here we have an alphabet which is consisting of only two alphabets or the symbols. And yeah, just to keep it simple, in today's lecture we will be mostly using the alphabet consisting of only 2 or 2 to 4 different symbols. So here we have an alphabet which consists of only 2 symbols, A and B, and then we have a regular expression, and which says that every string in this language or supported by this expression can should start with the letter A and B, and after that it could be either an empty string or it could be BA or it could be followed by AB. So this part is, because you have specified this part using the selection operator, so this part is an optional. Okay, so how many different strings can we find out or describe from this regular expression? If you have this regular expression, we say that in this regular expression we say that let's see if we have. So we have a regular expression with a small r, and then we have a root AB starting with the symbol AB, and then we have either it could be followed by empty string or the string AB, no, BA or AB. Okay, so it means this regular expression, this syntax specifies that this regular expression, in this regular expression you can only define the strings that starts with the symbol AB, and after that it could be empty string. So in that case, if we pick this one, so you get only this string. Okay, and then other possibilities is that, yeah, AB, and then we pick this, and we get the word ABBA. And if we pick this one, we get ABAB. We cannot skip this part. Every string or every word in that language will must have to start with this. Okay, so for example, if you want to find, if you have a file, a text file that contains a number of strings, and if you want to find strings that are beginning with A or B, AB, and then followed by either BA or AB, so you can do this by defining this regular expression. And then we have another regular expression where we say that start with the B, and then you can have 0 or more number of A's. Since there is no limits on this number of A's, so we can find an infinite number of. In this case, this is our finite language because we can only generate 3 different strings. However, in this language, using this regular expression, we can generate infinite number of strings. So it means that we will get an infinite language. And then the same goes to here because we have a star here, and it says that we can have double A or double B, and the star operator means that it could be 0. So we can skip any of them, and in that case we will get an empty string, because if we don't use double A or if we don't use double B, we can still get an empty string, which is a recognized concept, and then we can go on by making any combination. So for example, because this is I can use either double A or double B. So if I decide to use double A, I get this. If I decide to use double B, I get this. And if I can decide to use double A many number of times, I will keep on getting the different number of strings.
Is it possible to use, for example, let's say start with double A and then continue with double B?
Yes, yes.
Also
in the other way around.
in the second one, it's also possible to include empty string, right?
Sorry?
Is there also possible to include empty string?
No, because it must start with a B. You can, empty string could replace only this A, because star operator applies. If we have parentheses, and on the parentheses like this we have star, then of course you can have. But here it says that every word every string must start with a B, and then after the B it could either you can have A or you cannot have A.
And the last one, the third one.
Yes.
Where the
Yeah.
parentheses power of the star means we can assign the star each time to these two characters, these two words. For example.
Yeah, either this or either to this. Yeah, because you have a selection operator, R operator like this. And we say that R generates the regular language R, and the two languages are equivalent. Yeah, the two expressions are equivalent. Yeah, if and only if their languages are same. If two regular expression results in a same language, in a same number of strings, then they are we can say that the two regular expressions are equivalent. And here we have an exercise, so some work for you guys, just because I know that after looking at these examples, I hope you have got some understanding of. So if you can take your pen and paper, so maybe just give it a try and see if you really understand or not. So the first exercise, it says that you have an alphabet A and B, and you need to define a regular expression for all strings on this alphabet where the length of the string is an even number. So for example, you can have AA or AB or any length which is either 2, 4, 6, 8, or even the 0 is you can have that one. And then once you are done with this one, the second task is that you generate a string where the length of the string is odd number. So 1, 3, 5, 7. Could you try? anyone, I mean, if someone wants to voluntarily try. Maybe we can do this together. So with what should I start? Sorry? Yeah, even number. So I need to define a regular expression. R is equal to, and then what should I write? Parenthesis AB. Sorry? Ah, okay. On here or on?
No, on the whole of this.
On the whole of this.
Because we want to get
Okay.
right.
Sorry?
We want to get even number.
Yeah, we want to get even.
4, 6.
Yeah. Even the 0 is allowed. Yeah. 0, 2, 4, 6. Yeah. You're right. Or?
Again parenthesis and a star.
And again parenthesis.
Or
Or?
PB star. PB
Star?
star. Yeah, star.
Yep.
So true.
Yeah, you're going in the right direction.
Another one is BR also.
Yeah. Perfect. Yeah, you can do it. I mean, since you are using like star on all, so maybe, of course, this is correct. I don't say that this is wrong, but you can also write it like AB, or maybe, yeah, keeping it in a pattern like AA, and then AB, and then BA, and then BB, and apply, because you have a star on all the different 4 parts. Okay, but of course you can write it like that as well, so there is no problem. And now I hope everyone understands this one, because using this character, so it says that, yeah, for example, if you have a like this, we can get it by one choosing this part and one choosing this part. And if you have another, like starting with the BB, then BA, and A, so we can get by choosing this, because when you have star, it means that you can use the symbols or the strings many times. Okay, and then what about this one? Even odd number of, where the length is odd.
I think it's the same. You just cancel the parentheses. No, it must be 2 even. 2. I think the character A or B or A.
Yeah.
Yeah. If we have just even part, the even part must be followed with the odd part.
Yes.
Inside the parentheses.
Yes. So I think you're in the right direction.
Yeah.
So if we add 1A or 1B before an even length of string, we will automatically get an odd number. So if, for example, if you have a string of length 2 and then you add 1A, it's become 3, an odd number. And if you have a, maybe 100 and add 1A or B, you get an odd number of string. Okay, so that was really nice. So we have here we have the solution that we already have done this part. And it's important that you put the parentheses. Otherwise, this concatenation will get over this selection. And then we have a second exercise where you have an alphabet which consists of symbols minus, 0, and then a D, where D represents the digits from 1 to 9. And you need to write a regular expression such that R represents all integers. And you should remember that negative 0, 0 is 0. There is no positive or negative 0. It's a 0. So this is not a valid integer. And also, you cannot have more than, you cannot have zeros in the beginning, because normally, you can say that this is the requirement for this language, that you cannot have zeros at the beginning. So every valid integer that is required in this exercise, it could be either a 0 or a negative integer, or it could be a positive integer but not starting with the leading zeros. Could you try this one? Yes, should I start?
Yeah. Open parentheses.
Open parenthesis.
Minus D or
minus
D.
D
Or D.
or D,
Close parentheses.
close parenthesis.
Star.
Sorry, star?
Plus would be the perfect, because
Sorry?
I'm used to like using a plus for that.
Ah, okay. But could you, I mean, if you have something like for a plus, for example, like you have a plus, you can write it like this, I think, A, because this is like one or many.
Yeah, it's at least once.
Yeah.
So I'm used to like, if
You can write it like this, I guess. So if you want to write something like this with the plus, because this is not, plus is not a basic operator, it's more like synthetic sugar.
I know
So you can do you can get the plus by writing this. So if you, so could you?
it's a bit more complex, because if you write it like this with a plus, then afterwards you just use a 0 and a star in it.
Okay. Okay. So maybe let's see. I can try with the, yeah. So of course we say that according to this rules, we say that you cannot have zeros in the beginning. So it means, like, let's say if I start with the D, okay, like 1, 2, 3, we could have, I mean, we can start with the smaller cases. So for example, in smaller cases, a positive integer, like only with the one digit, 1 to 9. And then we could have, more than 1. So how can we specify more than 1? We could say that it's either D or 0, multiple number of times, okay? But we are missing the minus part. So maybe we could put it like this, minus R, and then concatenating it empty. This is like for empty. Because if you want to have a negative, you can pick the negative sign, and then this will become a negative number. If you want to have a positive number, you can pick, because this is a selection, so we can take empty string, and in that case it will become, and by putting this D in the beginning, we are preventing this case, because we say that in our language 0 cannot be at the beginning. So in that case, every integer will be either a negative or positive. It will be starting from 1 to 9, digits from 1 to 9. And then we have, 0 can come later. Do you think is it perfect one, or there is something missing? I think there is something missing. Could you find out what is missing? Which integer is not supported yet?
Minus 0 is the first minus, it will affect on the 0 here. Is it possible?
No, because we have a digit in the beginning.
Okay.
In the middle, we have a digit. You cannot go directly to this part. You must have, because this digit, this D says that D is equal to.
Yeah, we must define this D.
Yeah. Otherwise, otherwise you can go to the -0. What about, we say that we cannot have -0, and we cannot have zeros in the beginning, but of course we can have 0 as a standalone. Can we get 0 from this expression? Only 0? No. So we could have, and then we will get solve this problem here. So here we have the solution here. So okay. Moving forward, yeah. So we have, as you said, that I mean we learned about that we have 3 basic constructs, which are concatenation, selection, and star. But many tools that support regular expressions, they have some more operators, which are basically syntactic sugars, and you can define them using these. So for example, R plus says that 1 or more, and if you want to specify 0 or 1, you can use question mark with the R, or you can also use using the basic operators like empty. Empty means 0, and R means 1, only 1. And we can also write the sequence in an interval. You can do it like this, but you can also specify like starting from 1 and then, and similarly you can use also for, this can be used both for the digits and for the letters A, B, C, D, X, Y, Z. And then we have, here we have a regular expression which defines Pascal identifiers. And it says that in the beginning, the first letter can be alphabet A to Z, but then after that, you can use the digits, okay? And this seems to be a pretty long regular expression, and it might be difficult to read. So we can break it into smaller parts. So for example, we take this part, and we have a named subexpression with the letter. We say that this part is a letter, and we define it. And then we say that this part is 0 to 9 is a digit, and we define it. And then we use the combination of this, and to make it more readable and easy to understand. And you can do that for any regular expression by defining a sub-named expressions. And then, the next thing is, once you have defined the regular expressions, then we need to know, like, to find out if you want to write a program, and you want that program that you specify a string, and then you give it a regular expression, and then you want to find out that your program should tell you that whether this string belongs to that language or regular expression or not. And we can do this using a concept known as finite automata. And the finite automata basically is an abstract machine which is used to recognize whether a string belongs to a regular expression or not. And so for example, how can we do that? We will talk about more. Finite automata basically it's you can say that it's a computing machine or device which consists of finite number of states and finite number of inputs and outputs, and then the transition. So here we have these nodes. These are representing states, and we have the input characters labeled here, and then we have some transitions. If you know that the graph theory, and you already know that we have edges and states, the nodes representing the states. So for example, we have a regular expression which says that a string should start either with A or B, and then it followed by B, and then 0 or more number of A's, and end with the B. So if we have to define a finite automata with this, we know that we have to start from either A or B. Okay, so we have this initial state. So a string could start either with A or it could start with B. And since afterward we could have the second symbol in that string must be a B. So from this state and from this state, the only path that goes on must have a B as a label. And then we could have A 0 or many times. So it means that at this state we have to have something like a loop, where we could have many instances of A. Or if we have a 0, it means that it could directly go to the final state using this B input. Okay, so this is how you can transform your regular expression into finite automata, and then you can use this finite automata to recognize whether the string input string belongs to this regular expression or not. So for example, if we get, because this is if I have a language like this, A B A B, we can check if this string belongs to this regular expression or not by starting from the 0 from the initial state, and we take the first letter, which is A, okay, and we take this path A, and from this we go to the state 1, and from there we say the next letter is A. However, we don't have, from this state we don't have a path with the letter A. It means this is not a part of. If you don't have a path in the finite automata for that regular expression, it means that this string is not a part of, or it does not satisfy the regular expression. Okay. Otherwise, for example, if we have another string like starting with the B, and then we have a B and any number of A's, maybe 3 A's and B, and then we have another one like A, B, no, and then like this. If we have to check this one, so starting with the first one, we take this path B, and then we take this B, and then we have A, yes, there is a path, and then A, there is a path, there is a path, and then B, and we go to the final state. If we successfully reach from initial state to a final state, it means that the language is accepted. Otherwise, the string is not a part of that. And on the other hand, if we see the second one, starting from the initial state, we take A and we go here, and then we have a B, so we come here, we have a path, and then we have a B, we have a path, and we reach the final state. Okay, so this is how you can use the finite automata to recognize something called regular, the strings that are defined by your regular expression. And okay, so this is what we have defined here. Okay, if a string is accepted and you have reached the final state, then it belongs to that. If it has been rejected, rejected means that you could not reach to the final state, then it's not part of that language defined by the regular expression. Okay, and then we have basically I already told you that a finite automata, it's an abstract machine, and it basically consists of 5 things. We have a Q alphabet, and then this sigma, and then Q0 and F, and these are like Q is used to define, it's a finite set of states. So every finite automata is consisting of finite number of states. So you cannot have infinite number of states and infinite number of inputs or outputs. And then you have some alphabets like A, B we have in the previous example. And then you have a transition functions which takes a letter from the alphabet and takes from one state to another state. And then we have the initial state denoted by with this Q0, and this should belongs to this is a part of this finite set of states. And in one automata, finite automata, you can have only one initial state, but you can have multiple number of more than one final states depending on your language. Okay, so and then we have 2 different kinds of finite automata. One we call deterministic finite automata, and another one is non-deterministic. The difference between the 2 is that in the deterministic finite automata, we will have at most one possible transition from one state to another state. From one state onward, we will have only one possible transition. It means like if you have a finite automata, like this is your 0, and then you have state 1. So from this state, you will, with the letter A, you can only go to one state. In this case, this is our deterministic automata. But if you have another path using the same alphabet A, that can lead you to another state, and such automata is known as non-deterministic automata, because for the deterministic finite automata, the condition is that you can, with the one symbol, you can have only one possible transition with one input. But on the other hand, if an DFA is not, if a finite automata is not deterministic, then it automatically becomes a non-deterministic. And in the DFA, you know, the empty string transitions are not allowed, because if you have an empty string transition, then you can reach to more than one states. Okay, and if you can reach more than one states, then it means that you are not deterministic. We will see the examples of both, like deterministic and non-deterministic finite automatas. Usually the NFAs or the non-deterministics are easy to build up, but they have problems. And the DFAs, they are a bit tricky to build up. So for example, here we have an NFA, and we have a regular expression here, A R B star and A B B B. And if you have been asked to build or develop finite automata, most probably you will get with this one. Okay, the A or B start, because we need to start from A or B, so it means the initial state we have the inputs A or B, and then since they can come 0 or more, so we have a loop, and then it should end with A, B, B. Okay, in the end, so these are we have here. However, if you develop a transition graph, like from one state to what other states you can go with the alphabets A or B, if you see from 0 state, we have more than one path with the label with the symbol A. When we get the A, we can either stay on the same state, or we can go to the state 1. So in this case, if you have more than one states in your transition graph for any state, then you have NFA. Okay, and so something that you need to notice is here is like that multiple transitions possible for one input. So here you can see that for the input A, we could have multiple transitions. We can either go to this state, or we can keep on that state. And and an NFA accepts or recognizes an input string. X if and only if there is some path from start to final. So that's the basic rule that we have. If you cannot reach from start initial state to the final state, then that string does not belong to that regular expression that is represented using a finite automata. However, I mean, every NFA, if you can have an NFA, for every NFA there exists an equivalent DFA. So it means that we can transform an NFA to DFA. However, it's a bit tricky. So for the same regular expression, if you want to get a DFA, which means that for every input you could have only one transition from one state to another. So then this is one of the way. Don't ask me that how I get with this one, because that's not my work. I just used it as a copy work. And here, if you look at here, for example, starting from the 0 state, initial state, if we have a letter A, we come here, and then on that state, you cannot find any state where you have a same letter and you have more than one transition. So in that case, so you have only one possible transition for each input, and no transition possible, then it's that doesn't belong to that part. And here is we have some algorithms here, and starting with a simple one, DFA recognition algorithm. So how can we use how can you write a program to find out if regular expression belongs to, and if you use, I mean, the first step is that you have a regular expression and then you transform it to a deterministic finite automata DFA, and then from that deterministic automata you can find out whether that string belongs to your regular expression or language or not. So we have basically 4 items. You need to know which one is the initial state, so you can have a variable for that, and then you need to know what are these final states, because to recognize a string, we need to know that if you are able to get to one of those final states or not. And then we need to define a method, the next character, which reads the strings, and starting from the first character, it gives us one character one by one. And then we need to define a method which takes initial state, and then from that state, if we have a character C, it gives us the next state. Okay, so here we have an algorithm for that. We defined a Q, which is equal to initial state, and then we have this method next character, which returns us. If you, for example, if you have this string, and if you want to test it, so this next character in the beginning will give you A. And then we have a while condition, which we say that keep on getting reading the characters from this string until you get end of file or end of string. And then we have a Q and this move function, and it updates our state from initial state to the next state by reading character C. Okay, and then we keep on doing this, and if in the end we get to the final state, if the Q is one of the final states, it means the string is accepted. Otherwise, you should display that string is not accepted in that. And there is equivalent Java code for this move method. So it has 2 parameters, state and next, and then you have multiple cases depending on your automata, the transitions from one in your finite automata. And you can use your transition table also to build on the transitions. Okay, so here is a summary of finite automata. Some of the known concepts are that there is a theorem about by this guy Klinis, and it says that for every regular expression there is a corresponding finite automata. So if you have a regular expression, you can transform that regular expression into a finite automata, and the other way around. If you have a finite automata, you can transform it into a regular expression. And for each NFA, there is a corresponding DFA. If you have because NFAs, as I said in the beginning, they are easy to develop. So if you have NFA, you can write a DFA. However, there is some differences about NFA and DFA. So NFA, they are easy to construct. However, they are more expensive. And they are also small in size, and doesn't require a large number of memory, because if you see in here in the example, you can look at here, because you have only few states and few transitions. But if you look at the equivalent DFA, you have still the same states, but you have many more transitions going on here. So normally it says that to develop or use an NFA, you need a little amount of memory, and this is usually proportional to the time. The complexity of that is proportional to the length of the regular expression, so the number of symbols that you used in that, and the time is also proportional to the length of regular expression, and also the multiplied by the length of string that you need to recognize. However, in the case of DFA, if you have in the worst case, it could be proportional to the 2 raised to power of length of r, and the time is, however, this is more expensive. The DFA is more expensive in terms of memory usage. However, it is very fast to recognize a string. The time complexity is quick, because it can recognize the time complexity is proportional to the length of the string that you are going to recognize. But in this case, it requires less memory. However, it's a bit slow. It takes more time to recognize a string. So the conclusion is that NFAs are easier to construct. However, they are slow. And the DFAs, these are not easier, a bit tricky, to construct and develop, and also takes more memory. However, they are quite faster in operation. So if you need performance specific, if you want to recognize your string in a fast manner, so then maybe a DFA is a better solution. And here are some, another algorithm. So for example, if you get a regular expression, and we know that once you, for every regular expression, you can define an DFA, and for every DFA, you can also define a regular expression. So if we have a regular expression and you want to define a non-deterministic FA, so this is a bit similar. What you need to do is that you can start by defining two states, the nodes for two states, initial and so 0 and 1, and then you can write your regular expression here. So for example, if you have a regular expression like this, A, B, and A, B, B, and if you, and if you want to build a non-deterministic finite automata for this expression, you can start with the simple two states, and on the label you can put A or B star and then the whole regular expression. And then if you have some part in your regular expression which is concatenation, and for the concatenation concatenation part, you need to split this one, the concatenation like this. Add another state between the parts which are concatenated. And if you have a selection part in your regular expression, you can replace this, because you can go either with the A or with B. And if you have A star, there is a special rule for this. You can replace A star with this construct epsilon. Don't ask me like how can you do that like that. This is some built-in. This is some method by some smart guy. So I don't understand how he come up with this one. But if you use this, if you build it with exactly with like this, you will get the results that satisfy this star operator. Okay. So yes.
Why not use the loop to count one statement? I mean, you see one state, for example, 0.
Yeah.
And use a loop to
Yes.
count the 0.
Yep.
Not use that. So why not use so complexly?
Yeah. Yeah, you're right. Maybe give it a try and see if you get the similar results. It might be that the easiest solution, but I really don't know. And so, for example, we have a more detailed step-by-step over here. So we have this expression over here, and we take first this concatenation part, and we split this as this one, A, B, 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 B. Okay, that's straightforward. And then we have this star, and we apply this epsilon rule, and we get this E and this part. This is actually, I mean, this part is same, and however this part is that we get from this rule. It's basically application of this rule, where we have this epsilon for the star. And then once you have done this, in the end we can split this part, A or B. So we split this transition and added two transitions, for one for A and one for B. And in this way you get a non-deterministic NFA equivalent to this regular expression that you have over on the top. Okay, and then once you have, as I told you, that NFAs are easy to construct as compared to DFAs. They are more tricky and to come up, because you have to make sure that for every input at each state you will have only one transition possible. But there is another algorithm. So you can start first by having a regular expression, and then you can use this algorithm to transform your regular expression to NFA. And once you get an NFA, then you can transform it into a DFA. However, that's not a part of this course. So you will not, you don't need to worry about this. You will not be examined. This is more advanced concept. And for those of you who are a master students, you will learn this, this algorithm in the compiler construction course, this one, which will be offered in the next study period. So, and then, we could also have the other way around. So we have now learned that how can we transform a finite automata to a regular expression, but we can also get from regular, we learned that how can we transform regular expression to a finite automata, but then you can also do the other way around, from finite automata to regular expression. And we do this by deleting states one by one. So for example, here we have a finite automata, and we want to get regular expression from this finite automata. So if we have a three or more, if we have more than two states, then we remove the states and we keep only the initial and the final states, and we combine these labels together to get this one. So this will, and if you have a loop, you replace it with the star. And this will become more clear if we look at an example. So this is this example is from one of the previous exams. Okay, so the question is here, like you have this finite automata, and you need to convert this finite automata to a regular expression. Okay, and you might get some question like this in exam as well. So maybe in the question we give you a finite automata, and we ask you to give produce equivalent regular expression. And it could be the other way. We give you a regular expression, and we might ask you to provide us with NFA for that regular expression. Okay, so as we said, that the step is that you can in the finite in your regular expression, we start by removing one state other than the initial and final state, because you cannot remove initial and final states. So in this case, this is initial state. This is represented by some strange symbol, and this with the double circles, it's a final state. So we can either remove Q1 or Q2 and then combine and see. So here is some solution for that. So we have this finite automata, and let's say we decide to delete this state Q2. So in that means when we delete this one, but we still want to we don't remove this. So it means that when we are removing this, so we need to connect this one directly. So we do it like this. So we delete this state, and we add an edge from Q3 to Q0, and we put both these input labels over here, 1, 1. You got it? So it's not something complex. And then, so now we have 3 states. And the next step, we need to delete one more state. We cannot delete this, or we cannot delete this, so we need to delete this Q1. So when we eliminate Q1, so it means that we have to take care of these things and have to connect it with them. So so we have a path from 0, and then after the 0, we can read more than 1 zeros, okay, and then we followed by another 0, okay, or we can directly read from Q0 to Q3 using this edge. So that means we have 2 possibilities here for reaching from Q0 to Q3, and this we have specified like this, okay. And then from Q3 to Q0, we can go either this way, 1, 1. We cannot go from this way, okay, because there is no edge from Q1 back to Q0. And there was one way like this, Q0 and then transition, and then we come here. Another possibility is that we can keep on here, from here, here, Q3, Q1, and Q3. Okay? And for this, we added this part. We have 1, 1, 0, and then 0 can come many number of times, 0 or more than 1, and then we end up with 0. Okay? You understand this part? So it's for this and this part. And then you can also, once you get this one, you can replace them with some symbols, U, V, and you can simply come up with the notation here. This is your final result R, because U is equal to this one, and we say that V is equal to 1, 1, and then if you take this one, you get this one. Okay. I think I'm not going to take a break, although you might be tired, but I want to really finish this one. So hope it's okay for you guys. So now we have a context-free grammars. Okay, that's the final part in our lecture. We have learned about regular expressions, and I told you that both regular expressions and context-free language, they are used to define languages, formal languages, and but there are some differences that we will learn about that. A context-free grammar looks like this. It's basically consists of something like this. These are some transitions or rules, productions. So it says that the context-free grammar A such that it could have again an A or a symbol A, or A may be B. Okay. So from this we can define a language, because we know that this language can be defined from this context-free grammar. How? Because here we have the explanation. A, you can also read it like this. If you have to represent this in a regular expression, we will later on look at how context-free grammar could be represented in a regular expression. So from here we say that A leads to B, so it means that we can replace A with a B. And then we have an A. However, this A again, so in this A we replace A with a B and we get this thing. And then in this third step we have an AA, but with this A can be replaced by AA, and then you can replace, of course it's up to you, you can still replace this AA with another AA, okay? And in the end you will get something like this, B, B, A, B, A, B, A. So it means that the strings in this language will be starting with B, and then it could have 0, 1, or more than 1 number of A's. Okay. So it means that if we have a context-free grammar like this could be represented simply using a selection operator, A or B, and the alphabet for this language, it's basically 2, A and B, and this letter A, it's a helping symbol, and we also call this as a non-terminal because it's not a part of the alphabet. The basic building blocks of this grammar are A and B, and this A is only used as an identifier or kind of like a help symbol, and the alphabets that are used in a context-free grammar, we call them as terminals because these are the final parts, and the help symbols, these are known as non-terminals because they don't end up result in a real a part of a string or sequence or language. Okay, so and then if we have to define it more, maybe no, not here. Yes. So a context-free grammar, it's basically consists of 4 things. We have terminals and we have non-terminals, and then we have a productions, and we also have some start symbols. Okay. So in this case, terminals, these are basically your alphabet symbols A or B, and N is a set of non-terminals like the helping symbols that in a capital, and we usually write terminals in a small letters, and we write non-terminals in a capital letters. And then we have a productions, and the productions are basically the rules like this. When you have something like like this. So these are basically our productions. So it's like some kind of association between non-terminals and terminals. So it's a set of productions. So and this must you take one non-terminal, and then it can lead you to either a combination of both non-terminals and terminals. And and the S is a start symbol. So for in a context grammar, you must have to specify your the start symbol, which is basically a part of this non-terminals. Okay. So then we have some examples here. We already looked at. So here we have a grammar, and it says that B that leads to that could be parenthesis B, and then B, and then an empty string. Define the language of, and you can use this context-free grammar to define the language of balanced parentheses, because how can we get this from this? Can someone explain? Did you got the idea or not? So basically we have production rules here, and it says like B or BB or empty string. Okay. So let's see if we take this string and see if we can produce this string from this context-free grammar or not. Okay. So because these are alternative parts, so we can say that this is one part, this is second part, and this is third part. And if I take the second part, I can say that B leads to BB. And then if I take this one, part 1, and I can replace this with this part, and I can also replace this with this one part, and write again like this. And next I replace with the third part, which is an empty string, so you don't need, I mean, it's an empty. So in that way I get this part, and you can also get the other parts in a similar way. Okay. And and often we use these context-free grammars normally to write the syntactical part of your language. So for example, if you want to define the statements, and you have a construct called statement list, which consists of statement list followed by other statements, sequence of statements, or maybe only one statement. And what is statement? Statement could be a, depending on your programming language, it could be a while statement, if statement, switch statement, or any other statement. And then you can define what is while statement. And then here you use the keywords. These are the basically symbols of your language, and these are actually the help symbols. And then you keep on specifying and describing this in a continuous manner. Okay. Coming back to some exercise to fresh up and to keep our brains working, and also to test if we really understand or not. The first exercise, I think is the same that we used for a regular expression. Write a CFG, context-free grammar describing all strings S over AB such that S is, the length of the string is even. Could you try that? It's the same that we did for the regular expression, but now this time you have to do it using the context-free grammar. And also, meanwhile, if you want to try the second exercise, some of you, which says that write a CFG describing the language, A, and then raised to power I and b raised to power I, and I is more than 0, it means that simply we can say that the number of a's followed by the same number of b's. So it means that if you have a 1a, then you should have 1b. If you have 2b, then you must have 2b's. So the number of a's and b's in your string should be same. If you have a 3 a's, you must have 3 b's in the end. And if you have 4 a's, 5 a's, 10 a's, then you must have the same number of b's in the end. Anyone would like to give it a try? It's basically, I mean, the first part is more or less similar to the one that we have. So for example, let's see here, because we have a short time, so I don't want to. So we have, you see in the regular expression, we use this part, AA, AB, BA, and BB. However, we don't have this star operator in this case, but we know that this number of A's could be more. If we want to have more, then we put the A, and it means that we can get more. And then if we only want just 2 of A's, in that case we can replace this A with the empty string. Okay, and then similarly, the second exercise is a bit more tricky. Yeah, maybe we can do it like this. So in here we have A, and the base case in this case is that we have A and B, 1A followed by 1B. However, we say that we can have 2, 3 A's, 3 B's, and we can get that part by having this expression, the next free syntax. How can we get this part? Using this context-free grammar part. Let's say we start with this one, A, B, okay, and then we replace this A again with this part, so we get another A, yeah, A, B, and then B, and then we again replace this part with this, so we get another. No, now we need to replace it with this part because that's our last step. You understand? However, yeah, can we? I mean, we already seen that we can represent this in a regular expression, but what about this? Can you write a regular expression for this? Any idea? I mean, we have tried already this thing, but we have not tried this in a regular expression. So one approach to write a regular expression is that maybe we can define a finite automata for a language, and if we can define a finite automata, maybe we can get a regular expression as well. So let's say we have a state, and we can start with an A, and then we say that A must be followed by B. Okay. So in this way we can get this part, and in this case, let's say we say that this is our both initial and final state. Okay. This is our initial and final states. We cannot stay here. However, what about this one? A, B, but we are in the final state. We cannot get one. And if yeah, sorry. Yeah, for this part, that's So we A, B, B. However, the problem with this solution is there is no final solution, because I mean this satisfies this case, this satisfies this case, but if I add another B, then I have to add another, and if we keep on adding the number of B's and A's, we have to keep on adding and adding. So it means that we cannot represent this in using a regular expression. Yeah. So this shows that some limitation of regular expression as well. So the context-free, you cannot define a language regular expression for all the possible different strings. So you can only have for limited number of strings. But as compared to regular expression, the context-free grammar provides you with more power to define the different strings. Okay. And we have already learned about these parts of context-free grammars. And the productions, these are the form of these rules. And here the A and C, these are the terminals, and the B and D, these are non-terminals. So here we have grammar for arithmetic expressions. So for example, if you need to define a set of all arithmetic expressions involving only the plus and the multiplication. So for example, you have 3 different expressions. So this language could be described in this case as we see that here in the context-free grammar we have 4 parts. We have terminals, we have non-terminals, and P and S. And so here we can see that our terminals for these, they are for these 3 expressions, they are basically A, B, C, and these plus multiplication symbols, and then we have this small parentheses and opening and closing parentheses. And then we say that our non-terminals consist of only the letter, the symbol E, helping symbol E, and this helping symbol E, because we have only one terminal, so this is also our start symbols. And and here we have the P part, set of productions. So we could define these different arithmetic operations by these different productions, A or B or C, and E leads to E parentheses plus multiplication. Okay, and now you have this context-free grammar, and if someone asks you, can you show that this A plus B star C, it belongs to this, is recognized by this context-free grammar, the language defined by this context-free grammar or not? Could you show that? So the string we have is S is equal to A plus B multiplied by C, and we have 4 different production rules. So where should I start? Which rule should I pick? Let's say I pick the rule 3. Can I pick the rule 1 in this case? Can I pick the rule 1? No, because if you pick the rule 1, then it means that you can either, if you say like this, A, B, or C. With this rule 1, you can pick only one of them, either A or B or C, and you don't get this one. So it means that, and can I do this? Parenthesis? I don't think so, because I don't have a parenthesis in my string. So maybe I can take either this or this. Okay. So if I start with the, let's see, I think we have a solution here as well. So these are our rules. So I start with the 3rd rule, and I say that E plus E, and then on the next step, I apply the rule 1, and I replace this E with A, and then I get A plus E. Okay, E plus E. This was rule 3, and then I applied rule 1, and I replace E with A, and I get plus E. So I have solved this part, but I still need to solve this part. So which rule should I apply next? 1. Why? If I apply the rule 1, I will get either A, and which letter should I pick? For rule 4, yes. We cannot, if you take the rule 1, yeah, finally, but not now. So, and then, yeah, we do it like this. And the rule 4 says that, and then finally, as you said, that we can apply rule 1. And then in this case, since this is B, so we pick from the rule 1, we replace E with the B, and in this E we replace with the C. Okay? Oh, sorry. So this is some explanation of, and we call this thing as a derivation. We can do a derivation to show that. So this is basically, we are deriving. We have a start symbol E, and then we use the productions to derive strings. Yeah, and there are two kinds of derivation. We have a leftmost derivation and a rightmost derivation. And the difference between the two is, in this case, if you see, I first derive the left part. Here I derive this one, and then I go to the right part. So in the leftmost derivation, you start from the left part and replace it with the terminal symbols. Okay, and in the right, you do it the other way around. You, instead of, for example, if I do it like this, if I have E, E plus plus, E, and then if I want to, but then, yeah, maybe I have to choose start with the rule 4 if I want to apply the rightmost derivation. Okay, because then I have to start with the on the right side with the multiplication part. And then there is also the concept of parse trees, and the parse trees, these are graphical representation of derivation. So here we derive it like this, and you can also do the derivation in using a tree-like a structure, and we call it parse tree, and it's often used by compilers to recognize your code. And you might be familiar with the concept of syntax trees or abstract syntax trees, which are generated by your parsers or compilers to recognize your code. And if we have this derivation, we can represent this derivation in a form of a parse tree. And how can we do that? So we're starting from start symbol E here, and then we split it E star, and so you can represent it here. Okay, and then so this is equivalent to this step, and then we have a E star C, and so we can do it E star E, and this ID is basically representing the C, the symbol. Okay, and then you have this E plus E. So here we have reached to the final point, to the final symbol. Then we need to replace this one, drive this one. So we do it like this, E, and we replace it with the E plus E, this part. And then we replace this E plus, this, and this one, if you see, is it a leftmost derivation or is it a rightmost? It's a rightmost derivation, because we are first driving the right, the symbol, and then we go to the left part. Okay, so that's the difference between leftmost derivation and also. So you see the example you see here, it was a leftmost derivation, but what you see here is a rightmost derivation. Both are, I mean, there is no much difference so in results. So, and then you have you have some more exercises. We have over here. We have some context-free grammar here, and you need to show that you need to use the leftmost derivation and show that we can derive these parentheses from this context-free grammar. Could we do that? And you need to use the leftmost derivation. The language, the context-free grammar we have is B or BB or empty string. And I call this part as 1, this part as 2. So these are production rules. This is rule 1, so 1, 2, 3. And the string we have is S is equal to parenthesis and then inner parenthesis and nested parenthesis. And the rule we need to apply is the leftmost derivation. Okay. Which rule should I start with? Sorry? With 2. Why with 2? We have only 3 rules. 1, 2, 3. No fourth. Yeah. With 2. But why?
Because we want to have a multiply.
Yeah, it's more like concatenation kind of thing here. Yeah, you're right. Yeah. So the important part is if you pick a starting point right, you most likely will end up in a right way. So this is the most important part. So if you pick up the right starting rule, you will get up to the right.
Start with 1.
Then with 1. And so I replace leftmost derivation, so I can replace this one with B and then B. Okay, and then next, which rule? Rule 3. Because if I apply rule 3, this B will be replaced by empty string. So we have got this part here, and now we need to get this part. So which rule should I apply next? What? Who said 1? Okay, you all agree 1. And then who says 2? I heard something. Okay, yeah, doesn't matter. So we again apply the rule 1 and then 3. Yeah. So and in this way you solve that one. Okay. That's exactly something like that. And then we have another one. Show by leftmost derivation that this A star B plus C can be derived using grammar 1. Let's see how much time we have. We have only 5 minutes. So yeah, it's basically the same rule. So you can apply. The important thing in this is that you start because it's a leftmost derivation. So and it involves the multiplication sign. You start with the rule 4. And if you started with the rule 4, you most likely you are going to achieve the results. And then we have a parse tree. So if you have this rules derivation, and you already see that you can replace this rule derivation and you can represent it in the form of a parse tree. So for example, here we have a B, and then we replace with the BB. Here we have a BB, and then we replace this B with the B, and then we have 3 children of this. And then since in the end, after doing this, we replace this middle part with an empty string. So we replace this B part with it. And similarly, you can do it for the other part as well. Okay. Yeah, and then we have a parsing problem, and we have a number of different techniques. Yeah. So the parsing problem or the parsing technique is that algorithm for finding a derivation of a given input. And at each step of the derivation, choose the correct production to apply. So you have already done this. So basically, this algorithm, you need to define an algorithm for this. So and the important thing is that you need to start with the right step, and at each step you pick a correct rule. And there are different approaches here. And some of the common approaches, we have a top-down approach. and we have a bottom up, and then we have a universal approach. And the difference between them is, in the top down, you start with the, like here, you start with the from the top with the start symbol, and then you go down. But in the bottom up, you usually start with the leaf nodes, and you go to the up to the root node. And usually in the top-down approach, we use the leftmost derivation starting from the start symbol. But in the bottom-up, we use normally use rightmost and the backward rightmost derivation starting from the bottom. And both this top-down and the bottom-up, they are easy to use and develop. And however, they can only handle a limited set of strings or grammars. You cannot use it for, but they are easy to use and fast to develop and recognize. And then there are some other specialized cases of these top-down and bottom-up parsing algorithms that they are more powerful. However, they are very slow to use. And you don't need to worry about in this course about them, because if you are a master students, you will get more details about them in the compiler course, because there in the compiler course you will be actually writing your own compiler, a mini compiler, and then you will be learning these techniques as well and using them. So and also an important concept is here is in the context-free grammar is the ambiguous grammar. It's what does it mean? That it means that if you have a grammar and you can from that grammar you can derive multiple two or more than two different parse trees, then your grammar is not unambiguous, because it leads to more than one parse trees. And so in that case, your compilers may be confused in which one is correct and which one is not. So for example, here we have the two rightmost derivation of a plus b multiplied by c. You can have, starting from this multiplication, you can get this one, and you can also get it by starting from the rule a plus, and this you still be able to recognize this part. Okay. And whether a grammar is ambiguous or not, it's not a property of derivation, but it's rather a property of your grammar. And also, however, if you have a ambiguous grammar, you can transform it into an unambiguous grammar. So, for example, here the grammar that we have that we used it here, this one, this resulted in an unambiguous parse trees, or it's an unambiguous grammar. However, we can transform it to an unambiguous grammar, and by defining, by using the correct precedence of different operators. So, and the starting symbol is in this case is the E, and then we have the help symbols and the alphabets. And then we have some production rules. And if you have these production rules, you can get this parse tree. Okay. And then we have also some exercise, show a leftmost derivation using grammar 2, this grammar. And here we have the rightmost derivation. But can you show the leftmost derivation? Yeah, it could be done. If you start by e plus t, this rule, and then t plus t, which is you apply, you replace this e with this t, you apply the rule 1, and then finally you will end up with the right string. And then also an interesting problem with the context-free grammar is that if you have an unambiguous grammar, you usually get the problem known as dangling else. So what is dangling else? So for example, you have this grammar for if statement, and according to this grammar, we can get this code or this code. And in this case, which one is the correct interpretation in most languages? So this else belongs to this if or this if. looking at these two different interpretations.
The first one belongs to the previous string. Yeah.
The first one belongs to
Previous string.
the nearest one. You mean the inner one?
As I see here for the index belong to, it must belong to first if, but
You mean to this?
yeah, but it's not maybe happen for the
But usually in most of the languages, the inner else is belongs to the nearest if part. Yeah. So usually, I mean, if it's a Java, I mean, of course, in different languages they have different interpretations. But if it's a Java, then this else belongs to this if part. So this is an example of where unambiguous grammar could result in different interpretations, and then the compiler or the user might be not sure which one is correct. Okay, and then here is some summary of context-free grammar versus regular languages. And as I told you in the beginning, the regular language is a smaller part. It's a subset of the context-free language, and the context-free grammar is more powerful. Whatever you can define using a regular language, you can do that also using a context-free grammar, but not the other way around. If you can define something in the context-free grammar, it may not be defined in a regular expression or regular language. And you have already seen the example of this A's followed by the same number of B's. And also this matching parenthesis, we cannot define this using regular expressions. Okay, and usually, I mean, if you talk about the programming languages, we normally use context-free grammars to define the syntactical parts like class definitions and statement specifications like for the different iterative statements and selection statements. But we use for low level like identifiers and variables and keywords, we use these are normally we use regular expressions because they are more suitable for this kind of constructs. And then, however, although the context-free is more powerful than regular expression, but it also has certain limitations. So, for example, even if you have a string which is whose length is the x raised to power n, where n is a positive power of 2. So, for example, and what is the positive power of 2? It's like 1 positive power of 2. Yeah, 2 itself, 4, 8, 16, 32. And if someone asks you that define a language which has strings of this length, positive power of 2, and it's known problem with the context-free grammar. You cannot define it. And similarly, if you have something like int variable plus string variable, that's usually it's not allowed or cannot be defined using the context-free languages. So these are some limitations. So, and then here is some hierarchy of languages. So. At the lowest level, we have regular languages, and then we have context-free grammars, which are usually more powerful than regular languages. And at the bottom, we have the natural languages that we speak in daily life, like English or whatever language you speak. And these are the most powerful languages we use. And these languages are these hierarchies was defined by this guy Noam Chomsky. Have you heard about him? It's an American scientist, also computer scientist, but also known as for his criticism about the U.S. government, on the U.S. government and its policies. And it also has done a lot of work in the languages. He's a kind of, you can say that, a linguistic guy as well. Okay. So this brings us to the end of today's lecture. And in the next lecture, and as I said in the beginning, maybe some of you guys joined late, so I will just repeat it. This lecture was the last lecture from the content point of view, but in the next lecture you will get details about examination, and that lecture will be given by Dr. Jonas Lundberg, who has been teaching this course for many years before me. And I will also upload sample questions, sample exams from the previous year, so you can just go through and see, get an idea that what kind of questions we will have in the final exam. Okay, and also the assignment 4th will be uploaded by the evening. Okay. So thank you very much, and good luck with your future studies because I may not be able to see you in the next lecture. Yeah. Thank you. Thank you.